And welcome to another CPD seminar for graduate engineers. This time we'll be talking about precast concrete walls, or tilt-up panels or tilt slabs, as they're sometimes called. The procedure follows the New Zealand Code for Concrete Structures, NZ 3101, as well as the CCANZ guides IB82 and TM34, as well as a guide from Branz. And yes, it's another one of those seminars asking what does this spreadsheet do, and given the answers in Mathcad. So we have two Mathcad files. They're both quite large and quite complicated, so I'll try to drop through those as quickly as I can. The first one is about tilt panels or tilt slabs and how we design for out-of-plane behaviour. We'll look at the design as a propped cantilever for wind and earthquake, as well as the design as a cantilever for the fire situation. We'll do some detailing checks for shear, work out what the connection load is at the prop, and a design of the foundations. We'll have a check on the thermal cracking and look at the design for lifting of this panel, as well as the anchor design. Second file goes into the design for in-plane behaviour. That says you can use a tilt slab as a shear wall. And first of all, we'll look at the stability, i.e. Euler buckling and lateral torsional buckling. We'll also have a look at the foundation design, connection checks, and so on. Here are the references. It's IB82 from CCANZ and TM34. So that's quite a useful tilt-up technical manual. So if you haven't seen those, have a look at those. Also was inspiring into this presentation was the Branz design guide published in 2007 on slender precast concrete panels with low axial loads. Obviously we've got the concrete standard, and for lifting and anchors we look at the Reed concrete lifting design manual. So I won't go into the theory and practice of precast concrete because I've already done that in seminars 10 and 11. So go check those out on the Danny Pig YouTube website. And while you're there, why not subscribe to the channel, hit the like button, and obviously share it with your friends. So here is our red coat spreadsheet for tilt panels or tilt slab walls. And I won't go into a great deal of detail on that. I'll be going into the Mathcad version. And just a reminder, there's a nice little diagram in that red code spreadsheet, which you can cut and paste into your calculations. So we'll begin with the out-of-plane behavior in Mathcad. So let's open up Mathcad. And here is the Mathcad for the tilt wall single-story propped cantilever. So we begin with entering the basic information such as the height, thickness, and the panel width, also the footing width and thickness. Put in some basic parameters for the concrete and the steel, as we would normally do for concrete design. Add some details for the rebar, for the walls, and the footings and the slab. So then we get to the loading. So we've calculated the loadings in the normal way with reference to 1170. And let's go into the design for the in situ condition. So first of all, we look at the panel as a propped cantilever. And this is for the design for wind and earthquake. And so we derive what the nominal load is and take that as a simply supported panel and being conservative. We do a quick check on whether the system is stable. Have we got high axial loads? And we can calculate what the maximum applied load is and compare it with the limit. They're talking about a limit of 0.015 FC. We're much lower than that, so we can say we can use a simplified analysis and carry on. So then we need to calculate the moment at the mid-height of the panel, and we do that assuming conservatively that it's simply supported. So we derive the earthquake load and the mid-span bending for that. We derive the wind load, and then we find out what the mid-span bending moment is for that. In this case, 5.29. So the maximum moment is 7.14 as the earthquake dominates. And what's the load, the axial load that goes with that? Well, it's 12.57 kilonewtons per meter. So we now work out what the capacity of the wall is in bending, looking at the steel force, deriving our lever arm and our compression area. From that, you derive your moment capacity as 13.6 kilonewton meters using the equations given in NZS 3101. Now, we might look at the concrete section either as uncracked or cracked, but chances are in the ultimate limit state, your concrete section in the wall in bending is likely to be cracked. Now, equation 11-5 of the code gives you this equation for the second moment of area of the cracked section. Now, there are a number of ways of calculating the cracked moment, second moment of area for a concrete section. This is just one of them. We'll look at some more later. And from that, you can calculate an enhanced moment. And from that, you can then calculate the mid-height deflection and compare it with a deflection limit. We're saying 2.5%. It seems quite high, but hey, that's what the code says. And then we compare our enhanced moment. And again, it's working out as 8.55. It's just happy coincidence they work out the same. So our utilization ratio is down to 63%. So we're good in bending. Now let's have a look at the moment at the base and regard it as a propped cantilever. So here we have the moment for the earthquake condition and the wind condition. And we want to know which is the maximum. In this case, it's earthquake. And we have our utilization ratio of 52%. Then we move on to fire. So many of these tilt slab walls are used as boundary walls. And if it's on a boundary, it may be used as a firewall. Now, practice in New Zealand is such that you don't want to fire protect the whole building if your boundary wall can stand up on its own in a fire. And to do that, it needs to act as a cantilever. So we take the lateral fire load as 0.5 and work out what the moment of the base is. So our utilization ratio is 78%. Now, the guidebook TM34 gives you minimum thickness for the equivalent fire rating as well. So we've got a thickness of 150 millimeters. You could possibly push it to an FRR of 180 minutes, but you'll use a bit lower than that. Now, considering the temperature inside the concrete and therefore the temperature of the steel inside the concrete, we can then work out some cracking or whether the section is cracked under the fire condition. So we take a fire duration, in this case of 1.5 hours, at a maximum fire temperature of 660 degrees, and this is taken out of IB82. And from that, we get the moment at the base of 38 kilonewton meters. From that, we get our concrete tensile stress as 1.97. However, our applied bending stress is 2.56, which means our concrete is cracked in the fire condition. So we have another equation to work out what the cracked section modulus is, and that's from IB82, and they're just saying let's take 0.3 of the gross section. And using that, we can work out what the deflection is due to the fire, and then looking at the depth to the steel, in this case it's pretty much in the middle, and work out what the steel temperature is using the formula given in IB82. From that, we can calculate what the concrete modulus is. In this case, it's the same as the normal concrete modulus, but the steel is slightly smaller in the fire condition as it's got a raised temperature. Work out what the fire modular ratio is by comparing the modulus for the concrete versus the modulus for the steel. Our steel yield strength remains at 500 MPa. Let's move down. We then create a transformed section based on that section modulus and the modular ratio. That allows us to calculate the fire curvature and the fire strain. From that, we can gather the axial elongation as a small number of millimeters. We'll assume, for simplicity, that the foundation doesn't rotate, and so it's a fixed base in effect. And that allows us to calculate the deformation of the cantilever. In this case, it's 87 millimeters. In the fire case, we're using a strength reduction factor of 1. Again, calculate the steel force, the depth to the stress block, and from that you can derive the moment capacity, which we find is sufficiently large to allow the applied bending moment. Now, IP82 gives some consideration for P delta effects. So this is second order effects. Your wall has moved, so therefore the axial load is eccentric. And there's another formula for the second moment of area for the cracked section, and that's in IP82. And we can use that to calculate the deformation of the cantilever, and that gives rise to the additional moment. So the total moment is now 41.9 kilonewton meters, which is still below the capacity. A quick look at the detailing. The Branz guide gives us a table 1, which gives us the minimum and maximum steel percentage. So we just check our steel ratios against the minimum and maximum, and we'll find that we're okay. Moving down, let's look at the shear capacity. And again, we're looking at earthquake, wind, and fire. And what is our maximum applied load? We've worked that out from above. And what's our maximum applied shear? So we take the shear area as 88% of the gross area of the section. And then the concrete shear stress is taken from the New Zealand code. From that, you can derive the concrete shear strength, which is 104 kilonewtons per meter. There's also steel that's potentially taking the shear. So we add those together and add a factor of safety. That gives us a total shear capacity of 113 kilonewtons per meter, which is more than sufficient for our applied shear load. Now, there's a connection at the top because the roof is basically tied in to the panel. So we've said it's a prop cantilever under earthquake and under wind, but it's a cantilever under fire conditions. But even under fire conditions, there's still a connection there to consider. And so therefore, we need to design the connection for a maximum of the force resulting from the face load due to the fire, 0.5 kPa, the force required to develop the nominal flexible strength at its base, and the force to ensure that the wall fails inwards under fire. So there's our notional fire load. Looking at the shear arising from the moment capacity. So what shear do I need that can carry the moment capacity of the panel? And then look at the wind load and look at the seismic load. And then we derive that the maximum load we're looking at is 22 kilonewtons. We want to make sure the wall fails inwards. There's another equation given in IP82, which tells you that the connection force, therefore, is 10.97. That's lower than the figure we've actually designed above. Moving on to the foundations. Again, we're designing the foundations to resist a maximum of the wind loading on a propped cantilever, earthquake loading on a propped cantilever, multiplied by the overstrength factor, because we don't want the foundation to fail first. And also look at the fire loading on the cantilever base. So the overturning moment from these loads is going to be resisted by the weight, basically, of the slab, the foundation, and the wall itself. So when earthquake loads are governing, we put a overstrength factor in to avoid potential plastic hinge zones. So the overstrength factor comes from the code NZS 3101 as 1.35. We've worked out what our axial load is from above, and so our overstrength bending moment is just simply multiplied using this equation given in the code, equation 2-10. Now we have a small slab that's on the edge of our foundation, and we've derived what the slab bending capacity is based on the equation here. So we need a length of slab to resist the overturning. So the stability of this tilt panel wall is not just relying on the foundation, but also the slab it's connected to. And so we need to know what the shear is at the end of that footing. So we've calculated that here, it's given as 5.57 kilonewtons per meter. So now we look at the overturning moment at the base of the wall from the earthquake and the wind as a propped cantilever, and then from fire as a cantilever. In this case, the fire is the dominant load case here. So the overturning moment is going to be the maximum of those, and those calculated above. We look at the total length of the base, which is width of the lower pad plus the outstanding footing. That works out as 2 meters. And from there, we can calculate the weight of the footing and the weight of the wall as counterbalances to the overturning moment. So we need to take moments about the base of the footing, that's point O, and we find the restoring load. So our restoring moments are calculated simply by the weights multiplied by the lever arms, and we get a maximum restoring moment of 19 kilonewtons meters per meter. Now to do this, we work out what the reaction location is. So this is where we look at the position of the reaction underneath the foundation when given that overturning moment. This allows us to calculate the bearing, simply the twice the length of the location distance that we've calculated above. And from that, we can also look at the maximum bearing pressure that we're going to derive in the soil, which works out as 79 kPa. This is lower than the design bearing pressure from the figures above. Now let's look at the reinforcement for the design in bending of the footing. So we take our wall bars down into our slab. So we work out what the footing effective depth is. So it's 300 thick footing, but we've got cover and therefore a bar to reduce. And the footing capacity is based on the wall rebar and works out as 45 kilonewton meters per meter. And thankfully, this is less than the overturning, and this is more than the overturning moment. Then we also do a check at a meter or slightly short of a meter from the wall, because it's based upon the capacity of the footing rebar alone. So we've got no more wall rebar in there. And that works out as 18.12 for bending outwards, and for bending inwards, we have 5.8. So our capacity based on the footing rebar works out as 18.85, which is thankfully greater than the applied bending for overturning. Quick look at thermal. Now, tilt panels or tilt slab walls exposed to the sun will be subject to elongation, expansion due to the increase in temperature, more importantly, the temperature differential from the inside to the outside. So we take our coefficient of thermal expansion from the code, and then we work out the tensile stress given by the code. So the temperature difference, that's the difference in temperature between the outside and the inside, is 15 K, which is equivalent to 15 degrees at C difference. So the deflection at the midspan of the unrestrained panel due to this temperature difference is given here as 5.75 millimeters. And that 15K is the maximum temperature before the concrete starts cracking. And this is the maximum deviation before the concrete starts cracking. So we want to restrain it. And to restrain it at the bottom, we need a force WT 5.83. Taking the calculation full circle, we've got the moment at the base of 33.68, which gives us a stress of 2.25, which matches the limit. So therefore, okay. So if our temperature difference is more than 15 degrees C, then we need to think about how it cracks up. Quick look at the design for lifting. Now, many structural engineers won't be doing the lifting design, and it's often left to the precast concrete manufacturer. But here from the TM34, there's some guidance to how these panels are lifted. The reason they're called tilt panels is they're cast flat and then tilted up. So it's possible to cast a large, thin, slender panel on its side in a way you couldn't do it vertically, and then lift it up once it's cured. Now, the turnaround time for these panels is a day or two, so they'll be probably lifting it up either a day or 2 days after it's been cast, which means it hasn't reached its full design strength yet. And so you're looking at a reduced strength of concrete, which means you're looking at a reduced tensile capacity in that fresh cast concrete. There's a guide in the panel tables, and that tells you what the tensile stress is when you're lifting. But we can go to the calculations for this in more detail. So we have our wall properties, work out the weight of our wall, it's 97 kilonewtons, and as above, the tensile strength of the concrete is 2.25. Now, let's look in the longitudinal direction first. We're looking at the gross section modulus of the wall panel. And for a single row, when we're picking it up, we're looking at a basic pickup in the middle towards the edge here, which means our support moment MA is 39.2 kilonewton meters. Our mid-span moment is 39.14, very similar. And the stress arising from this is 2.61, so that's slightly bigger than our tensile strength. So therefore, a single row isn't enough. We need a double row. So let's look at a double row, slightly more complicated calculation for that, but it's basically a continuous beam. And so you've got lifting at point P with what's working out the loads. We put a factor of 1.4 on the self weight, by the way, just in case. And then we can derive what the anchor load is because we've got 2 rows in there. Looking at it as a continuous beam, we can calculate what the support moments are and the span moments. And from that, we can get the stress at each of these points and see that the maximum tensile stress is less than the concrete tensile strength. So the double row is what we need. Now, looking in the other direction, the transverse direction, we take a beam strip of your wall panel and we make the width of that beam strip 13 times the thickness, or 0.4 of the height, 40% of the height. So that's where you derive your beam width, and from that you get your section modulus. For a 2 pickup, we can work out what the tensile strength is, and now we look at a 4-point pickup. And work out what the support moments and the central span moments are in those cases. And just to show you a little diagram of the bending moment diagrams going on here. This is basically our continuous beam. This is our tilt slab being picked up on a lifting beam and on a crane. Now let's look at the anchor design. And again, normally it's the precast concrete manufacturer that will do the anchor design, but we can have a quick look at the Reed Concrete Lifting Design Manual. So we've got our panel weights and we've chosen the number of anchors as 6 for our purposes. And the reason we've done that is because the anchors are not particularly strong. Face anchors are not particularly strong. And there's a whole load of factors to use. One of them is the adhesion factor, and it depends what you're putting it on. So Reed give this guidance is to increase the factor, the rougher it is. So if I turn that into rough timber, my HA factor goes up to 3. Let's put it back to smooth steel. Let's put it back further down. And we have a demolding factor. So again, it's a function of how rough the surface is that you're demolding from. Normally in a precast in your yard, you're casting against smooth steel. There's a slinging factor. So remember from previous CPD seminars, the bigger that angle, the greater the anchor load is going to be. So ideally you want an angle of about 60 degrees. If you go bigger than that, our slinging factor goes up to 2. So let's say 60. We've also got a dynamic load factor, a KD, for this. For normal operations, it will be 1, but if you're going to transport the thing on its anchors across rough ground, it's going to be 4. That makes quite a big difference. And the way you handle it makes a difference, whether you're doing a standard crane or an excavator. So then we calculate the effective load given by this equation from the guide, and that gives an anchor load of 2.5 tons, rounded up. And so we pick an anchor. In this case, our anchor has got a working load limit of 4.13 tons. So we can go for that. So here is a product specification for that anchor, and we need to check the edge distances and so forth for that. So that was the out of plane behavior. Let's move to the in plane behavior. So this is the Mathcad for the tilt wall single story as a shear wall. You're looking at in plane behavior. So we've got our standard parameters as we had before, the wall thickness, height, so on, size of the foundation, some properties for the concrete and the rebar. Let's scroll down through that. You've seen this before. And our loading is similar to the loading we had before. Loads from the roof, loads from the wind, loads from earthquake, and so on. So it's basically the same configuration, but we're also using it as a shear wall. So there's loading in the plane of the wall. So our Branz guide, it gives us 4 checks to do. The first 2 are relatively simple. It's just a height versus thickness. And the first is easy to do. Is our height over thickness bigger or smaller than 75? It's smaller, so we're okay. Then there's a modified thickness depending on the configuration, depending on the fixity at the ends. Now the design guide gives you a table and a diagram as to what's going on. So there is an out of plane deflected shape for these slender walls. So you're likely to deform them out of the plane, but if you're loading them, they're also going to deform out of their plane. And the factor that you're looking for there is dependent on the fixity of the wall, whether it's going to be normally fixed at the base, possibly pinned at the top, or no support at the top. Now let's close that and look at the Euler buckling. So the Branz design guide gives you this formula for working out what the Euler buckling factor is. And we compare that with a modified height to width ratio. And if we're within that, so our slenderness is less than 98. So we're okay by that Branz equation 1. Now let's look at the lateral torsional buckling. And there's yet another formula taken from the Branz guide. So we've worked out what the design moment is at the base of the wall due to the out of plane loading. And then our lambda is worked out as the minimum of these two equations, and we compare it to a modified slenderness ratio. So here is a diagram of that out of plane buckling behavior that happens due to in-plane loading. In effect, you're looking at a beam, and a beam which is narrow and deep may buckle out of its plane due to its in-plane loading. Let's move on to the connections and the foundation design. So there are two approaches to it, depending on where you are in New Zealand. Different areas prefer different methods. First method is the drossback, dowel bars and a drossback duct, and the guide gives you some development lengths or guidance on the development lengths you need, and the maximum splice bar bend spacing you can have. And then we'll look at the alternative, which is sidebars in effect. So you have horizontal start bars coming out of the wall panel. Now these can be cast in and bent out on site, or they can be inserted into cast-in sockets. We first do a shear capacity check. Now we've worked out what the shear force is on the panel from separate calculations. So we've considered the whole building and the loading from lateral loading down to the base of our shear wall. We've said it's 18.3. Now 18.3 at the top of the wall gives an in-plane moment of 118 kilonewton meters on that panel. And we've got a nominal concrete shear stress of 0.93 from our New Zealand concrete code. We're using 80% of the gross concrete area for the shear area, and therefore we have a wall concrete shear capacity of 446. So we're already seeing that our concrete shear capacity is well in excess of the applied shear. So therefore, minimum horizontal shear steel is required, and the amount of steel required is quite small. Let's look at the bending. So we're looking at in-plane bending. So we have quite a long lever arm. Don't forget, we've got a 4-meter long panel. So we take a lever arm as 2/3. These are all fairly crude rules of thumb, but they seem to work. And from that, we can work out what a compression force is based on the moment derived from above. And from the compression force, we can work out what the concrete stress is. So at 0.3, it's well below the reduced concrete capacity. Let's look at the steel. So we have 16 bars, potentially 16 in tension. And we've got 2 rows of them in this case for the starters. And we work out what the maximum bar force is, given the applied load, what the shear is per bar, and what the resultant force is. The resultant force is a mere 5.6 kilonewtons. We've got an area of 113 square millimeters resisting that shear at that interface. Now, design shear strength can be enhanced by the applied load on the top of the wall, but for the purposes of being conservative, we can ignore the loading and reduce it to 0. We're also taking the friction coefficient as 1, which gives us a design shear strength of 42 kilonewtons. So looking at the foundation, so we work out what the vertical shear forces are in the foundation. Look at our effective depth of the foundation. Remember, this is a 300 deep footing. And look at what the foundation shear area is. So we're taking the shear over the full width of the panel. And the shear force in the foundation works out 29.7 kilonewtons. The maximum shear stress we can have is 6 MPa, but our concrete shear stress works out as 0.55. That's from the New Zealand code again. So the shear resisted by the concrete is 623, simply because it's such a large area. And our concrete shear capacity, given a factor of reduction factor, is 201. So in this case, shear reinforcement is not required, but if it were required, you can work it out as to what areas is required and what spacing is required for your shear links. Final check on the bearing. So we've got a triangular stress distribution with a compression zone worked out as half the panel length. So the maximum bearing stress under the footing is given by this equation here and works out as 24.78 kPa, which is significantly less than our design bearing capacity of the soil. Okay, so that was the Mathcad for the in-plane and out-of-plane behaviour of tilt-up panels. A reminder of the references, and finally a pause for questions.